Hello friends, today we will discuss the experiment of Malus law. The aim of the experiment is to verify Malus law of polarization and to determine the relation between the intensity of transmitted light through analyzer and the angle between the axes of polarizer and analyzer. Let us see the apparatus used. It consists of a diode laser. Uh, this is a diode laser and a polarizer and an analyzer pair, a dial fitted with the polarizer, a photodetector which converts the light falling on it into current and measured using a microammeter. All these things are mounted on an optical bench, and this is the unit for power supply of the laser. Polarization is the property of light that specifies the geometrical orientation of the oscillation. As we know that light shows the dual nature, it shows the particle-like nature as well as a wave-like nature. So light is considered to be electromagnetic wave which is transverse in nature, and polarization is the only phenomena which confirms the transverse wave nature of the light. So when light propagates in a direction, electric and magnetic field vectors oscillate in a direction perpendicular to the propagation of light as well as perpendicular to the each other. So here we will be discussing only about the direction of oscillation of electric field vectors. So electric field vectors are in a direction perpendicular to the direction of propagation. If we restrict it in one direction, that is known as the polarization of light. Here a light beam is shown moving towards right. The direction of oscillation of electrical vectors are shown with yellow and blue color. It is passed through a polarizer having its pass axis in vertical direction. So when light is coming out, only yellow vibrations which are in vertical direction, they are allowed. The blue ones are restricted, so they are not coming out of this. So this is a polarized light. Now let us see the geometrical representation of the polarized and unpolarized light. So here we have considered that the light is coming out of this plane. It is moving in this direction, and these are the direction of oscillation of the electric field vectors which are in all possible direction perpendicular to the direction of propagation. So this is an unpolarized light. The other way of it is, if we assume that these are the vertical direction of the oscillation, and this dot shows the direction which is perpendicular to this vertical and going in and out of this plane, and the light is moving in a direction from left to right. So this also shows the unpolarized light. Here we have shown the only one direction of vibration, that is vertical one. Light is moving from left to right. Similarly here the vibrations are from in and out direction. So these two, the lower ones, they represent the polarized light. Now let us see what happens when an unpolarized light falls on a polarizer analyzer pair. So this is unpolarized light falling on a polarizer having its pass axis in vertical direction. So the vibrations of only vertical direction are permitted. So this is a polarized light falling on the analyzer which has its pass axis crossed to the polarizer, that is at an angle of 90 degrees. So we get absolute dark or no light at all. But if the analyzer has its pass axis inclined to the polarizer at some angle, then so let us see that this is the pass axis of the polarizer, and so the vibrations are allowed in this direction. So when this light falls on the polarizer which has its pass axis in this direction, so the horizontal component of it, which is a cos theta in this direction, they are allowed to pass through, whereas a sin theta are blocked. So we get an intensity at the output which is less. So this intensity of the transmitted light is given by IT is equal to I naught cos square theta, which is also known as Malus law. Where the IT represents the intensity of the transmitted light, that is through the analyzer, and I naught is the intensity of the incident polarized light. Now let us see the experimental setup for this. This is the power supply for the laser. This is the polarizer. This is the analyzer, photodetector, and its output is measured in terms of current in microammeter. So they all should be mounted at the same height and along the same axis. To start with, we adjust our analyzer and polarizer pair to get the maximum current, that is the maximum intensity. Ideally they should be the angle should be 0 degree, but sometimes there may be some offset which should be accounted for. So we'll note down the maximum current and the angle at which we get the maximum current. On the left upper side you can see the dial fitted with the analyzer, which we are changing to get the varying current. And on the right upper corner you can see the intensity at the photodetector. So you'll see that if we go on increasing the angle between these analyzer and polarizer pair, the intensity and because of the intensity the current goes on decreasing. We can see that the spot on the upper right corner is decreasing with the increasing angle, and at when the relative angle between the analyzer polarizer is about 90 degrees, the spot is almost diminished, it is 0. Then again it is increasing when we go on increasing the angle beyond that. So that is when the polarizer analyzer pair is crossed, the light intensity is 0. But when the angle again increases, the intensity increases. So in this way, in a 360-degree rotation, we see that the two times our intensity becomes maximum and two times the intensity becomes minimum. So we'll keep on taking the readings, and at least for one complete rotation, that is for 360 degrees, and try to take readings as close as possible to get a better graph. I have taken some readings. In first column, I have written the observed angle between the analyzer and polarizer. And as we saw that there was some offset between these angles, that we were not getting maximum at 0 corresponding to 0 angle. So that angle should be subtracted from each of the readings to get the actual angle between the analyzer and polarizer. So now let us discuss our results. With the help of the observations, we have plotted a graph intensity versus theta, and we see that it gives maximum output at maximum intensity at 0 degree and minimum at 90 degrees. It again increases when the path axes are parallel to each other at 180 degrees, and then further decreases at 270 degrees, again gives minimum. So one complete 360-degree rotation, it follows a curve IT is equal to I naught cos square theta. So the relative intensity of the light emerging from the analyzer, it becomes maximum at 0 degrees and 180 degrees, whereas minimum at 90 degrees and 270 degrees. So if we plot an intensity, experimental intensity versus cos square theta, so it gives us a straight line as expected. and with the slope indicating the incident intensity of light. We also plot an I experimental versus I theoretical, where theoretical value can be calculated as I max cos square theta. So it can be seen that it is a straight line which shows the validity of Malus law, and it agrees within the limits of the experimental error. So these are the results we get from our observed readings. Now let us see what precautions we have to take while performing the experiments. So the first thing is that the laser light should be handled with utmost care. The analyzer, polarizer, laser and detector, they all should be at same horizontal level and along the same axis to get the appropriate readings. Then analyzer should be rotated by very small angles so that we get a proper shape of the graph. Then experiment should be performed in the dark room because light may uh, change the values of the current. Then photo detector is a very sensitive device, so it should be adjusted well at the appropriate height to receive the maximum current. Thanks for watching. Hope this will help you.